Hey, welcome back. In this video, we're going to start discussing set theory. We're only going to go into the basics. There's a lot of set theory. It could fill up a whole semester course or more. In this video, we're just going to start talking about sets and classes, and we're going to discuss a paradox that happens if you're not careful about how you define sets. Starting out, we're going to discuss classes because they're actually a little simpler than sets. Classes are just collections of elements that are defined by a property, and that property has to be satisfied by all of the elements. So these classes contain all of the elements with that property and only the elements with that property. On the other hand, sets are a type of class, but they're special, so they have more restrictions than just classes. Every set is a class, but we're going to see in this video that there are some classes which are not sets, and they get a special name. They are called proper classes. And like I said, we'll see an example of a proper class in this video. It's probably the most famous example of a proper class, but actually there are many other examples of proper classes. If we have some class or set, let's give it a name, we'll call it capital C, and we have some X, which is an element of that class or set. There's a notation that we use which is very short, much shorter than writing out the words X is an element of C. We write X and then this symbol right here, the epsilon symbol, and then C. And that says that X is an element of C. A shorter way to say it is just X in C. And here are some examples of using the elementhood relation. For a true statement, we can write 0 in R, where R is the real numbers. And that's true. On the other hand, we can also write a false statement involving the elementhood relation -1 in N, the natural numbers. And we know the natural numbers start at 0 and go up, so they do not include -1. If we want to define a class, we can define it in a very simple way, regardless of what property we're using to define it. So let's say we want to define some class C. So C is the class we're trying to define. And we're defining it as a set of all elements X for which some property is true. And we'll just give the property a name. Our property will be named f of X. And that property f, it only has one free variable, which is X. So if there are any other variables which are mentioned in f, they are bounded by some quantifier. So we can write our class C, instead of writing it out in all those words that we saw in the second bullet, we can write it simply as C equals squiggle X colon f of X. And words that's saying that C is the set of all elements X for which f of X is true. So that colon right there, you can think of that colon as saying for which. So now that we have some notation for elementhood and a shorthand notation for defining classes, let's get into the paradox, which involves how we will define sets. So we can talk a little bit about history. Around 100 years ago, so back in the early 1900s, they had different rules for how they defined sets than the rules that we use today. Specifically, they thought that it was possible to define sets the same way that we just defined classes on the previous slide. And the rule they had for forming sets back then, it has a special name. We'll talk about it. It's called unrestricted comprehension. And we're going to see why unrestricted comprehension leads to very bad things, or at least things that are very bad if you're trying to make a theory that is useful. So, like I said, unrestricted comprehension, it's bad, for sets at least. And specifically, it's paradoxical, a certain kind of bad. So back around 100 years ago, in the early 1900s, they thought that if you have any property f of x with one free variable x, and you define the class, which is x, such that x is a set and f of x is true, they thought that class is always going to give you a set. And we're going to see in this video that actually sometimes you get classes from that which are not sets. So in general, the idea they had 100 years ago does not work. And the paradox that we're going to discuss in this video is known as Russell's paradox. It's probably the most famous paradox about set theory. And Russell used this unrestricted comprehension to get a really bad paradox. So how did Russell do this? The proof is actually very short. The main idea is really just defining this special class that messes up everything. So Russell defined this class, we'll call it C, and C is the class of elements X for which X is a set and X is not an element of X. So notice right there, X is not an element of X. That seems like kind of a weird statement about X, but it is just a statement f of X. It's just a property of X with one free variable, the X. And as long as it's a property of X that we can write with one free variable, we can put it and use it in unrestricted comprehension. And unrestricted comprehension tells us that this class right here, it's not only a class, it's also a set. And that's what's bad about unrestricted comprehension. It's going to lead us to a paradox, this C being a set. So we're going to get this paradox by considering two possible cases. And the cases will depend on whether or not C is an element of itself. And again, in order to get the paradox, we are assuming that C is a set, because that's what unrestricted comprehension tells us. And we will get a paradox on the next slide. So I'm writing the definition of C at the top again, just so we don't have to look at it on the previous slide. And we will consider two cases here. And again, I'm going to mention that the paradox that we're going to derive here, it fully depends on what unrestricted comprehension tells us, which is that C is a set. And again, that's wrong. That we don't want C to be a set. It messes up everything. But unrestricted comprehension was what they were using 100 years ago, and that's why they got a paradox. And we're going to see how that works. So like I said, we'll do two cases. And case one will be the case when C is an element of C. And that means case two will be the opposite, when C is not an element of C. So for case one, suppose that C is an element of C. And we wrote that with the elementhood relation, so I've written it in words on the next bullet. And if C is an element of C, we can look at the requirement for all elements of C up here. Elements of C must be sets, and they must satisfy that they are not elements of themselves. Those are the only two requirements. So C must satisfy that property. And that property, little typo right there, this should be a lowercase x. So I'll write that x not an element of lowercase x. And what does that mean? Since C is an element of C, and all elements little x of C satisfy x is not an element of itself, that means that C is also not an element of itself. And what's the problem with that? So we have C is not an element of itself, but for case 1, our assumption was that C actually is an element of itself. And those two together give us a contradiction. So that completes case 1. We showed that for case 1, if C is an element of itself, this leads to a contradiction. Now we need to do case 2, and we need to show that that also leads to a contradiction. So case 2 will have the opposite assumption as case 1. For case 2, we will assume that C is not an element of C. Now, by unrestricted comprehension, we're assuming that C is a set, because unrestricted comprehension tells us that anything that we define this way, where we take all sets X with some property f of X, unrestricted comprehension says that always gives us a set. So we're assuming right now from unrestricted comprehension that C is a set. So for case 2, if C is not an element of C and C is a set, then that tells us that since it's not an element, but it satisfies this part, the being a set part, it must not satisfy this part right here. So C is a set, but not an element of C. So it does not satisfy that property on the right, that it is not an element of itself. So it must not satisfy the property that C is not an element of C. And again, right here, same typo as above, that should be a lowercase x. So we want C to not satisfy this property. So C does not satisfy for case 2, because C is not an element of itself. And that means if C does not satisfy that, then C must be an element of itself. Because if C does not satisfy the property X not in X, then that means C does satisfy the property X in X. So C in C. And again, for this case, like the first case, we get a very similar contradiction. Because our assumption was that C is not in C, and then we just derived that C is in C. So in both cases, we got a contradiction. This tells us that the statement C element of C has no truth value. So we just showed that. And that's the paradox. So this is the whole Russell's paradox. And what's the problem with this paradox, or with any paradox in general? So like I said, having a paradox, it's bad for proving things. And specifically, it gives a contradiction in all possible cases, and it lets you prove contradictions from that. Why is that? Well, we saw something in an earlier video, which is closely related to this. And what we saw is that if you assume a contradiction is true, then you can prove any statement from it. The way that we can write this in propositional logic is we can write it as P and not P. So there's a contradiction right there. For any proposition P, P and not P will be a contradiction. And this implies Q for any proposition Q. So if you have a contradiction, you can prove any proposition from that contradiction. And I'll note, we can prove Q, we can also prove not Q, because that Q on the right can be any proposition. It can be Q or it can be not Q. So if we have a contradiction, we can prove everything from it, everything and its negation. So every proposition in the language of our theory is both true and false if we assume a contradiction. And this is bad because if we use the old axioms of set theory, we get a contradiction, and we can prove every proposition and its negation in the language of set theory from those old axioms. So those axioms don't tell us anything useful because they say that everything is both true and false. So they're useless. But the good thing is there is a fix, and the fix is pretty simple. So we talked about unrestricted comprehension. The fix is just to restrict the comprehension, and it's called naturally restricted comprehension. And the way we can define this rule is we can say that if S is a set and f of x is a property with one free variable x, notice that this part is the same as before. So this part did not change. This right here is the new part. So if we have if S is a set and f of x is some property with one free variable x, then we can define this, which is a set. And this is the set of elements x, which are elements of big S, which we know is a set, and which have the property f of x. So let's quickly go over the differences between this and the unrestricted comprehension. So unrestricted comprehension, again, it told us that this class right here of all elements x for which f of x is true, unrestricted comprehension says that that is always a set, regardless of the property f of x. Now we can see an obvious difference there. With the unrestricted one, the elements of the set that we are forming, and when I call it a set, obviously it's not always a set, but in the old axioms of set theory, they called it a set, and that's what led to the contradiction. So the elements of that new set can be from anywhere with the unrestricted comprehension. So notice the only requirement here is that those elements x have to satisfy the property f. The requirements don't mention anything about where the elements x come from. So unrestricted comprehension, there's no restriction on where the elements come from. On the other hand, as we can see in that second bullet, for the restricted comprehension, there is a restriction, and that's why it's called restricted. And the restriction is that those elements that we are including in the new set, they have to come from the same old set. So we always start with some set S, and we only include elements in the new set if they are from S and they satisfy this property F. And if we do that, then that gives us a set, as far as we know. So of course, it's always possible that someday someone might find some contradiction with the current axioms of set theory. But as far as I know, so far they have not. So with this axiom of restricted comprehension, we actually do get sets, new sets from old sets specifically. And we can use this axiom to define what we will call subsets. So suppose that we use this restricted comprehension axiom to form a new set T from an old set S. Specifically, we can say T is a set of elements X for which X is an element of S and f of X is true. and we call T a subset of S. And here's an example of a subset that we've seen before in class, but not with this notation. So we can define the natural numbers as the set of elements X, for which X is an integer and X is greater than or equal to 0. And we can see that this is just an application of the restricted comprehension axiom to the set of the integers with the formula f of x, the property f of x being x is greater than or equal to 0. And that allows us to say that the natural numbers are a subset of the integers. And we'll see many more examples of subsets. And we'll also see more axioms of set theory. There are many more. And we'll go over some of them in the next few videos. And if you find set theory especially interesting, there's a lot of lecture notes online about it. So set theory can fill up, like I said in the beginning of the video, it can fill up a whole semester course or more. So there's undergrad courses in it, there are grad courses in it, there's tons of set theory you can learn. If you're interested in it, there's a lot of good lecture notes online. And if you have questions about where to find good notes, let me know. I'm happy to send some to you that I found. And I'll mention that in this class, since it's discrete math, we're covering a lot of topics in here. So we'll only give set theory a few videos, but it's a very interesting topic. So if you want to know more, just let me know. I'm happy to send you more info, or you can just find it on Google. It's pretty easy to find on Google as well. Thanks for watching.